Hello, Finn. Finn, good morning.
Good morning, sir.
Hello, Finn.
Good morning, sir.
Okay.
Hello?
Notes. Finn.
Policy of the Central Bank of Nigeria, led by the National.
What are those?
The likes of the Quasios was and the Olabados.
Hello, Finn.
I'm with you, sir. I'm with you.
You cannot answer.
I've been answering you since, sir. I've been answering you.
How come I've not been hearing you? Where did we stop in the last class? Where did we stop? We can't remember. All right, let's start. When we have about 20 people, we'll start. Right? Oh. Hello, Fee. Ah.
Sir, I'm here.
Okay. Okay, let's start. All right. Since they're not coming on, not our business. Beam design. I hope you are seeing my screen.
Yes,
Yes,
I
sir.
am, sir.
Yes, sir,
All
we
right.
can see.
Okay, beam design. Like I've given you, it says what? A beam is a structural member resting on supports to carry vertical what? Loads. Generally, beams are placed what? Horizontally. The amount and extent of external load which a beam can carry depends upon one, A, the distance between the supports and the hanging length from supports. B, the type of intensity of load. C, the type of supports. And D, what? The cross section and elasticity of the beam. It says what? The amount and extent of external load which a beam can carry depends on these factors here. So let's look at this. It says depends on what? A, the distance between supports and the overhanging length from supports. Look at this one. So let's look at it. This will now lead us to various classifications of what? Beams. Here you have a cantilever. And look at this. It says what? A cantilever beam is a beam having its end fixed or built in. You guys should take note. When you say fixed or built in means what? The same. And it means what? Not movable. No horizontal movement, no rotational movement, no vertical movement, right? That is built in or fixed. And the other end, free. So this is an example of what? A cantilever beam. A cantilever beam. It says, in other words, a cantilever beam overhangs its supports. So this is another type of cantilever beam. As long as you have something hanging over a support, it is what? Faye. So I was okay, Faye. I'm talking to you.
You can't cantilever beam.
A propped cantilever beam. This is a cantilever beam with a support provided at some suitable point of the overhanging end in order to resist what? Deflection, right? Okay. And okay, who can tell us what's the difference between this support of a propped cantilever beam, this one and this? We're just looking. Fee, did you read this note at all? Doc, I'm listening. I'm waiting for your reply. Fee,
Yeah.
I said
I probably to this point.
yes or no. Did you read?
No.
Simple. Don't lie to me.
Yes, sir.
All right, let's go. These are the classifications of beams, right? So you should be able to what? Name, sketch, and define. Name, sketch, and define, right? Simply supported beam. A simply supported beam is supported at each end. That is a beam having its end freely resting on supports, like what? Brick walls. And then you see simply supported. Then you have an overhanging, continuously what? Supported beam. Yeah. I hope you can see the difference between overhanging and continuously supported beam. Right? Okay, no answer, no problem. Exam will come.
No, sir, I can't see the continuous supporting beam.
This is it now.
Okay, sir. Okay.
Figure 5, this one here. This one with two supports at the middle and overhanging at one and at both ends. Yeah?
Okay, sir. Yes, sir. Yes, sir.
And it says what? It says continuously supported beam are supported by 3 or more support points. Continuously supported beams deflect less than simply supported beams of the same span because positive, negative bending cancel each other, right? Okay, good. Do you guys understand why? Look at this. A simply supported, why this continuous supported bend less than a simply supported? You get? Assuming now you have your bench. Look at this. Can you see the simply supported now?
Yes, sir.
Why is it taking you guys so long to respond now? I beg.
Yes, we can see, sir.
Can see.
Shut up. How long did it take you to answer? Nonsense. Types of loading. Just be looking. You guys are not serious. You are not reading. I mean, I'm your problem. Types of loading: pointed, uniformly distributed. If you want to understand, if you want not to understand, it's your business. Not serious at all. You were shouting that you wanted to resume. Now you resume, you cannot study. Rubbish people. Types of loading: pointed, uniformly distributed, and gradually varying. Okay. Pure bending, simply bending. I hope you are looking at it. You guys are supposed to read this thing. Me, I don't. You guys are joking with me. All right. Who is that? Whose microphone is making noise? You guys should take note of these equations that I've given a background color yellow here. You'll be needing them seriously. It says pure bending. If a length of a beam is subjected to a constant maximum bending moment and no shear force, then that length of the beam is said to be in pure bending or simple bending. The maximum bending stress for that part of the beam remains also constant. Maximum, you guys should take note. Take note of these two terms: maximum bending stress and what? Allowable bending stress.
Yes, sir.
Okay. Bending moment of any transverse cross-section of a straight beam is the algebraic sum of the moments taken about an axis passing through the centroid of the cross-section of all the forces applied to the beam on either side of the cross-section, of the chosen cross-section. Okay. You know here that your P is equal to what? Applied load, which is usually P represent what? point load.
Point load.
Mhm. And then then the L is what? The length of the beam, right? And then in this case here, W here. Okay, what's the unit of P? Unit of P will be
Newton
Newton.
per meter square.
No, Newton. Come get away. Newton or kilogram. Right?
Yes, sir.
Newton per meter square, that's distributed load now. That's what we're coming to. Here, small w, capital W is Newton, or kilogram. Then small w is Newton per meter squared, or Newton per meter, or kilogram per meter, or kilogram per meter squared.
Sir,
Yes,
the other W is, you wrote it in capital letters, sir.
I'm changing it to small c.
All right, sir.
So by the time you now multiply your small w by length, you now have your capital W. Understood?
Yes, sir.
Yes, sir.
Yes, sir.
So now let me ask you, if the small w is Newton per meter squared, what's going to be your this thing? That means it's per area, B.
Yes, sir.
Yes, sir.
Yes, sir.
That means your capital W is going to be what?
Newton per
Newton per
meter.
meter.
Yeah. What will happen to that L? You're going to convert
Still
that L
cancelled
to
out.
the area. It might be, okay, let's just say, assuming it's going to be small w times area. You get? Understood?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
I like this guy that is talking now. What's that guy's name? The guy, there's two guys talking now. What's your name?
Olatife.
Abola Emmanuel, sir.
All right. I want to be hearing your voices. Forget that thing.
Okay, sir.
Okay,
right,
sir.
sir.
He's not serious.
Yes, sir.
So look at this now. Look at this equation now. Maximum bending moment. Bending stress, sorry. You have your M, is an M max over S. And I want to show you. And you know very well, what is S? What's S? What's the meaning of S? S represents what? Huh? These people now don't chop
Yes.
forget. Oh, Jesus Christ of Nazareth. Distance. S is distance. You people, and wow. S is section modulus now.
Sir.
Shut up,
And
section
L is the
modulus. S is section modulus. Now, wow.
Sir, we thought this section modulus is Z. The S is
I
no.
told you before now that section modulus is either S or Z.
Oh, I only know it's in Z, sir.
Okay, what's the equation? Sure, tell us, what's the equation?
Sir,
Is what over what?
the max is the maximum moment.
Oh, Jesus. S is equals to what?
Maximum moment over
Keep quiet.
L.
S has a who can remember? S is BD squared over 6. Is it not?
Sir, is it B square over here?
Eh? You said what?
BD square.
Yes, BD squared over 6. That's section 1.
Yes.
Who is that person now? What kind of rubbish is-
Cooper, off your microphone, Cooper.
Ow. Why are some people so unmannered like this? Okay. Okay, let's come back here now. Look at your beam here. The total length of the beam is L. The load is acting at the center. That means the distance from the load to the end B and length and end A is what? L divided by 2. Since it is acting at the word center. Right?
L divided by
L divided by 2 now.
Oh, okay, sir. Yes, sir.
And then you have your normal reaction at A and reaction at B.
Yes, sir.
Now, if we take moment about point A, who can do that for us? If you take moment, you don't know. Okay, you are taking moment about, you should get the paper when writing this thing down. Moment about point A. Just write A and write a circle around it. Moment about point A. Okay, taking moment about point A, that is going to be, you first see what you're going to do. You first of all, you have to define your directions. Is up positive? If you take up to be positive, downward loads will be what? Negative.
Negative, sir.
Yes. Okay. Okay. Here is taking moment, bending moment about point B. But let's take about point A. So it's going to be the reverse of what you have in the notes here. So is your downward positive or upward positive? Which one do you want?
Downward upward positive, downward negative.
Okay,
Downward
so now let's
negative.
start. So that moment about point A is now going to be equal to what? P, what's the
Times
distance of
L over
P
2.
times L over 2? Yes,
Yes, sir.
that's the only load acting downwards, right?
Yes, sir.
Is equal to what? Is equal to RA times what? Times
L.
A.
L.
RB times L.
RB times L, sir.
Okay, sorry. RB times what?
L. L,
Times
sir.
L.
Good. That's PL over 2 minus RB times what? Times L.
L.
Is it?
Yes, sir. Yes, sir.
Very straightforward. It's just the opposite of what you have here. And then assuming that the length is divided into, let's say length is L over 3, and then this other side is L over this. Huh? How are we going to get 2 over 3? Right?
Yes, sir.
So It's still the same principle. As long as you know the principle of divided into 2, that's just it. Right?
Sir. Yes, sir. Yes, sir.
Since, and just note, as long as the P is acting at the center, RA and RB are what? Equal.
Okay.
So once you see a question that says the point load acts at the center of a beam, just know that the reactions are equal. Just divide the point load by 2. You have the reaction. You don't need to stress yourself.
I have the one.
Okay. And give a reason why you arrived at that. You don't need to do any calculation. No. Just like, since P is acting at the center of the beam, reaction at A and B, reaction at A equals reaction at B. And then since the length is divided by 2, so that's the point load divided by 2, RA, RB, simple. Okay, good.
So when the reaction A plus reaction B, when the point load is acting in the middle, is so if we add RA plus RB to give us P.
Of course, yes.
Oh, okay, sir. Thank you, sir.
Okay, now we are getting to it. This our stuff will end in 10 minutes. And so once it ends, you will reconnect.
Okay, sir. Okay, sir.
Okay. So the next point to look at now. Okay. Maximum bending moment will occur at the center of the beam. And this is given as this. Okay. All right. Take notes. So maximum bending moment is what? PL over 4. PL, see how it was arrived at. PL all over 4, right?
Yes,
now,
sir. Yes, sir.
you should know this equation. I want to shade it green. If you forget anything, do not forget this equation. Safe bending equation. That says what? F, that is what? Stress. Compressive stress.
Okay.
Bending stress, that's bending stress. Tabulated. If all should be greater than or equal to the design
Stress.
F. Yes. Which that one is what? M max all over section modulus. I will send the table to you now so that maybe you can look at, let me share the table so that all of us can see what, okay, let me see. Beam table, where is that table? Strength properties, okay, good. Yeah, I should hold on. Okay, it's coming up. Spin. She's sleeping. Okay, I've sent it to Finn. She will share the table. Okay, meanwhile, look at this table. Look at this table.
Yes, sir.
Go away. How long does it take you to respond? Yeah. I will talk after 5 minutes. Okay, very good. You can see the table, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, we have this table. There are 2 here. This one is table 1 says what? Dry grade stresses for groups of what? Species. And this other one says wet, green. Green means wet grade. Moisture content, look at the moisture content. This one, moisture content is greater than 18%. Why for the dry grade, it is what? Less than what? content of 18 or less. So usually you don't use less than. You usually use what? Greater than 18, equal to or greater than 18. Who can tell us why? Because when you use wood, when you install wood, wood does what? It loses moisture in service, right? So that's why it's usually better to install wood that is greater, that has moisture content of what? 18 or greater. So that by the time it loses its moisture, it will just fit in. But if you install wood that is drier, very dry, what happens? By the time it dries in service, what happens? That's when you have your windows twisting anyhow, your doors not closing anymore and all that. So now, where you have F tabulated, this is where you're going to get your F. And let me show you guys something. A beam, they say a beam is installed what? Horizontally, right? Along, so the force acts, you know, if you look at a beam, along the length of the beam, you have what is called the grains. That's the fibers. The fibers of the wood run along the length of the beam. So now the force, now if a force is now acting perpendicular to the beam, force is acting perpendicular to the beam. That's acting perpendicular to the what? To the fibers. So when you are designing for a beam, you use what? Compression perpendicular to grain. This grain here is referring to what? The wood fibers. Right? So for a beam, you only use what? Perpendicular to the grains. This is for beam. You use this parallel to grain when you are designing for a column, because you install a column what? Vertically. So the force is now acting on the face of the beam, of the column downwards. Right?
Yes, sir.
But for this thing, bending, look at this. You have bending and tension parallel to grain. You don't use this. What you use for beam here is this. And then you have modulus. Sorry. Yes, modulus of elasticity is the same for all the wood species, all the grade, the strength grades. Understood?
Yes, sir.
A question can be given to you, and what you need to is this table will be given to you. No value will be given to you in the question. You are the one that will come to this table and then select what you want to use. That is why Finn's answer might not be the same thing with Bolo Atife. Because you'll be given the privilege to select. Okay, they say now select. They say design a beam. You are asked to select the strength group. You can select strength group 1, while somebody else might select strength group what? 6. Right? If not, yes, I will decide to give you the strength group to limit you. Give you the strength group, and then look at this. You have grade percent. You have 80%, 63, 50, and 40. And I will say what? Choose any one that you want here. So it's likely that what Finn will choose will be different from what you that is talking will choose.
Yes, sir.
And once you choose that, you just keep on maintaining a straight line. You don't mix up the values because they're different. Okay, this is your stress here. This is your tabulated stress. Perpendicular to what? Grain. You see here, stress is perpendicular to grain. This is it. That's what you choose. All right. You will always make me talk, and I get tired so fast. Yes, sure.
Yeah, sorry, sir.
Okay. You can go away, Joe. You are the one that is even adding to my stress because you don't reply very fast. Very good. So look at this. Do not forget this equation that is what? That's in green. Because if you are asked to find let's keep on. If you're asked to design for a beam, you know what you say when they say design a beam? What it means is you should find a cross-sectional area, which is the face B and D, which is what I told you people to go and buy. I said you should buy what? 2 by 2, 2 by 2, and 2 by 4. That is what you are designing for a beam. If you choose it's not the length, because length, if you can always add length, but the face, the cross section, you cannot. So what you're basically designing for in a beam and in a column, the only difference is that a beam is horizontal, while a column is what? Vertical. Right? So, so look at this equation now. And from here, and you know very well that your M max, do not forget. Let me put this.